Picture the icon of the seas. It is 1,198 feet long. It stands 196 feet above the waterline. It carries up to 7,600 passengers, has 20 decks, 7 swimming pools, and a full water park bolted to its upper levels. It weighs more than 250,000 gross tons, and it is currently crossing open ocean. Your instincts say that objects should tip over. Every visual cue your brain has ever learned says tall, heavy, top-loaded things fall. A glass of water filled too high spills. A ladder leaned too far goes. The taller the structure, the easier it goes down. And yet, this 20-deck floating city runs through rough seas, heels in the wind, and comes back upright. Every time. So what is actually happening? The easy answer is size. Big ship, hard to flip. And most people stop there. But that answer is incomplete in a way that makes the real answer far more interesting. Because size alone does not make anything stable. What makes a cruise ship stable is a specific set of engineering decisions layered on top of each other, each one solving a different version of the same problem. And several of them are working against each other in ways most passengers would find surprising. This is not a boat that got big enough to stop worrying about the ocean. It is a machine that must continuously earn its stability through geometry, weight placement, physics, and active intervention. Every single hour it is at sea. Start with a concept that most passengers have never heard of. Metacentric height, abbreviated GM. It is the vertical distance between two invisible points inside the ship. The center of gravity, called G, and the metacenter, called mg, is the point where all the ship's weight effectively acts downward. M is a geometric point above it that describes how the buoyancy force moves when the ship tilts. When GM is positive, when M sits above G, the ship has something called a righting moment. Tilt the ship, and the geometry of water displacement creates a correcting force that pushes it back upright. The larger GM is, the stronger that force is. A positive GM is what keeps the ship from continuing to lean once a wave pushes it over. But here is where the intuition breaks. If G rises above M, even slightly, even temporarily, the righting moment disappears. The force that was pushing the ship back now pushes it further over. And the ship keeps going. Every ship has what engineers call an angle of vanishing stability. It is the heel angle beyond which the physics no longer works in your favor. Cross that line and the restoring force becomes a tipping force. There is no coming back from it. The ship will roll past horizontal and it will not stop. So the engineering goal sounds simple. Keep GM positive. Keep G far below M. Give the ship a large enough righting arm at every point in its journey that crossing the angle of vanishing stability becomes effectively impossible. But here's the first real twist. Engineers do not want the largest possible GM. In fact, they actively avoid it. A ship with a very high GM is called stiff. It resists rolling aggressively. When a wave hits, it snaps back fast, brutally fast. The corrective motion is violent. Passengers slide, glassware shatters. People standing in the corridors lose their footing. A stiff ship is technically safer in pure physics terms, but it is operationally intolerable. It would injure passengers on normal sea days. Nobody would book it twice. A ship with a lower GM is called tender. It rolls more slowly, heels more gently, recovers with a lazy, gradual motion that most people experience as natural sway rather than alarming lurch. It is physically more comfortable. It is also, by definition, operating with a smaller buffer between normal motion and the angle where things go wrong. Every cruise ship is deliberately tuned somewhere in that range. The engineers choose a GM that satisfies the legal minimums and gives them enough safety margin, while also keeping the ride pleasant enough that passengers enjoy themselves. GM is not just a physics number, it is a hospitality decision disguised as an engineering parameter. And that trade-off between margin and comfort runs through everything else that follows. The foundation of the solution is weight placement. The heaviest things on a cruise ship are located as deep in the hull as physically possible. Engines, fuel tanks, ballast, mechanical systems. They sit at the bottom because every ton placed low pulls G downward, increasing the distance between G and M, strengthening the righting moment. Meanwhile, everything light goes on top. The water park, the glass observation dome, the sun decks. not because designers wanted them there, but because their lightness means they do not catastrophically raise the center of gravity the way a heavy object would. The weight distribution of a cruise ship is essentially an inverted pyramid, dense and heavy at the base, light and open at the crown, designed so that the physics permanently favor recovery. The International Maritime Organization sets the minimum legal thresholds. The righting lever must remain above 0.20 meters at a heel angle of at least 30 degrees. The maximum righting lever must occur no earlier than 30 degrees of heel. Metacentric height must not fall below 0.15 meters. Those are floors, not targets. Modern cruise ships are designed to exceed them substantially because the margin is the point. Now the 5-layer system underneath begins. The first layer is the hull itself, specifically its width. The beam of a modern cruise ship, 225 feet on the icon of the seas, is not just a structural choice. Width directly determines the waterplane area, which is the footprint of the ship at the waterline. A wider waterplane area means that when the ship heels, the asymmetry between the submerged and exposed hull sections is larger, which means the buoyant restoring force kicks in earlier and harder. A narrow ship has to heel further before the geometry generates meaningful correction. A wide ship barely has to move. The beam is the first line of stability defense, and it is baked in before a single passenger boards. The second layer is one of the oldest pieces of ship technology still in use: bilge keels. These are long, flat metal fins welded along the lower sides of the hull, running most of the ship's length. They have no moving parts, no power supply, no sensors. They have been installed on ships since roughly 1870, and the basic principle has not changed in 150 years. When the ship tries to roll, water has to push past these fins to let it move. The fins add hydrodynamic resistance to the rolling motion, not enough to stop it, but enough to slow it and dampen it. The rolling energy dissipates faster. The ship returns to center sooner. The cost of operating them is essentially zero. They are still on almost every ship ever built, because simple things that work are hard to replace. The third layer is ballast. Large tanks built into the lower hull, designed to be filled or emptied with seawater in real time. As a voyage progresses, the ship's weight distribution constantly shifts. Fuel burns off, provisions are consumed, passengers change decks, cargo is loaded and unloaded at ports. Each of those changes moves G ballast tanks counteract that drift. When the ship leaves port, the stability officer recalculates the current weight distribution and adjusts the ballast configuration to maintain the target GM. It is an active, continuous process. The ocean does not get a static ship. It gets a ship that is perpetually rebalancing itself. The fourth layer is the one passengers most often hear about: active fin stabilizers. These are large, retractable fins that extend from the lower hull below the waterline on both sides of the ship. They work like aircraft wings. Sensors detect the ship's roll angle and rate of change. The fins rotate, generating hydrodynamic lift that pushes against the rolling motion, countering it in real time, the same way an aileron counteracts a bank in turbulence. On Icon of the Seas, the fin stabilizers reportedly weigh something in the range of 350 tons each. The rough size of a regional jet aircraft, moving continuously underwater, adjusting their angle hundreds of times per minute. Here's the twist most people do not know. Those fins do not make the ship stable, they make the passengers comfortable. The IMO is explicit on this point. Active stabilizer systems are not counted toward a ship's stability certification. The hull must be fully stable without them. When the ship is docked, the fins are retracted. At any moment, the fins could theoretically be switched off, and the ship would remain upright because the hull, the weight distribution, and the passive systems underneath are doing the actual stability work. The fins are layered on top of a system that is already safe. They exist to suppress the rolling motion that would otherwise make the voyage unpleasant. They are comfort engineering. The distinction matters, even if the marketing never mentions it. The fifth layer is anti-roll tanks, partially filled chambers of water built into the ship and tuned to its natural rolling frequency. When the ship rolls one direction, the water in the tank sloshes the opposite direction. A fluid counterweight timed to cancel out the motion. Passive, mechanical, zero power required when operating correctly. It is a system that uses the ship's own momentum against itself. But underneath all of this, there is a phenomenon that naval architects take seriously and that almost nobody on a cruise ship ever thinks about: parametric rolling. It is not about a wave being too big. It is about timing. Every ship has a natural rolling period, the time it takes to roll from one side, cross center, and return. If the ship is traveling at a speed where waves are arriving at the bow at roughly twice the natural roll frequency, the geometry of the hull changes in a repeating pattern that can amplify each roll cycle instead of damping it. The ship does not get knocked over by a single massive wave. It gets gradually wound up by a rhythm. Engineers model this phenomenon for every hull design. They run computational fluid dynamics simulations of millions of wave encounter scenarios before the first steel is cut. The ocean is treated as a statistical distribution of random forces, and the ship is built to survive the extreme tails of that distribution, the rare, violent combinations of wave height, period, and direction that most voyages will never encounter. The engineering holds in almost every case. But engineering has limits. In 1995, the Queen Elizabeth II encountered a wave in the North Atlantic, estimated at roughly 95 feet, about the height of a 9-story building. The ship survived. Passengers were thrown, injuries occurred, the hull held, and the vessel remained seaworthy. That incident is documented and real. It also illustrates something the engineering community understands clearly. The stability systems work within an assumed envelope of sea conditions. There is a sea state that exceeds that envelope. The QE2 found the edge. It held. But the edge exists. And this is where the final, least visible layer of the system appears. It is not a mechanical component. It is not a physical design choice. It is a decision that happens on the bridge, continuously, before the conditions ever get close. Modern cruise ships do not wait for dangerous seas. They route around them. Officers on board monitor meteorological data around the clock. Satellite imagery, NOAA feeds, wave modeling, storm track predictions. When a system is developing, the ship does not sail toward it hoping the stabilizers manage. The ship changes course. It slows down. It waits at port for a weather window to pass. The route is adjusted, sometimes significantly, to avoid the wave environments where the engineering would be most heavily tested. Avoidance is not a backup plan. It is the primary layer of the stability system that passengers never see, never feel, and almost never think about. The reason most cruises feel smooth is partly engineering and partly navigation. The ship is not just built to survive rough water, it is operated to avoid it. This reframes the original question entirely. When someone asks why waves do not flip cruise ships, the answer is not simply that the ships are big. The answer is that a large, interdependent system is continuously working. The hull geometry, the weight distribution, the passive keels, the ballast management, the fin stabilizers, the anti-roll tanks, the hull modeling done years before launch, and the real-time routing decisions made every day at sea. Each layer is solving a slightly different version of the problem. The physics, the comfort engineering, and the operational intelligence are all running simultaneously. And every one of those layers has a limit. The stability systems hold because the engineers build in margin. The margin holds because the operators protect it. The operators protect it because they understand, better than any passenger standing on a sun deck watching the horizon, that the ocean is not something you defeat. It is something you manage, carefully, continuously, with redundancy built into every decision. The person who boards a cruise ship sees a floating resort. What is actually underneath that surface is a stability machine tuned to a trade-off between safety and comfort, layered with 5 overlapping physical systems, monitored in real time, and quietly rerouted away from the conditions that would test it hardest. The waves do not flip these ships because the ships were designed, loaded, operated, and navigated specifically to ensure that the moment of vanishing stability and the point of no return that exists in every hull ever built stays so far from ordinary experience that most passengers will never once think about it. That is the hidden version of the ship you boarded. It was never just a hotel on water. It was always a machine solving a problem. You just could not see it from the pool deck.